You can go take a look if you want to. Okay. So is this not adorable? If I were to ask, I bet most of you guys have played with silly putty before. Okay. This actually reminds me of, I went out after this class and double-checked mantle, like, you know, the core, let's see, we have the core, then we have mantle, we have crust, right? We're going to kind of keep talking about that. And the mantle, actually, it's not really a liquid. It's kind of like a, I don't know, it's like a slow-moving rock kind of mantle. Okay, and in that sense, I guess, kind of, we have silly putty, and I could have brought silly putty, but you kind of picture if you go slow, it kind of moves, okay, with your movement. But if you go fast, it cracks. Okay, and that's kind of what we have with regard to that mantle, okay, the kind of the slow-moving liquid stuff. Core, mantle, crust. Lithosphere is kind of between the crust for sure, and a little bit of the mantle. Okay, so we need to actually kind of talk about all of our planets again, and we're kind of talk about kind of what's going on with regard to its surface and the mantle and the core. So just sort of like that, rocks actually can be deformed over time. I am amazed at sometimes the rock structures that are left by glaciers that actually came from the North Pole, came down to Missouri or beyond, and then retreated, okay? It's like those sort of things left their impact kind of slowly. I think that is so cool. All right, so one of the things about a planet is a planet needs to be spherical, okay? And this idea of taking something that's not spherical over time, if it's big enough, it will just kind of naturally, gravity will make it kind of smooth off the edge and it'll become spherical. So this could be anything. This could be the Earth, this could be Mars, okay, this could be Mercury, this could be a terrestrial planet, this could be a moon actually. You kind of see the three components we talked about. The blue thing is the, gray thing is the core, thank you, and then the red stuff is the mantle, yep, and then the kind of the tan stuff is the crust, yeah. So there's a few ways of getting energy from point A to point B. One of the things about our planets is that early on, and they actually were nice and toasty in the core for a few reasons, but they're nice and toasty. So you can kind of see actually, we said the mantle isn't liquid, but it's kind of liquid. And I looked this up and I'm like, even geologists don't agree with each other on it, right? So basically, the material can move, okay? And so you kind of see it moving from hot, and it moves up to closer to the crust, and it cools down. After it cools down, it will sink down, and it will heat up again, and it goes like this. It's called a convection current. It happens all the time if you have a lava lamp. You get a little light bulb down there, okay? And what that does is heat up like the liquid near the light bulb, and once the liquid gets warm, it kind of expands and it becomes buoyant, less dense, and it rises. Once it rises, it cools down. As it cools down, it sinks again. Okay.
Is pressure more the closer you get to the
that's
core?
the other thing is as you get closer to the middle of a planet, the middle of a star, the middle of anything, basically the particles are closer together and the pressure is higher. Yeah, the stuff is more dense and it's higher pressure down there.
So the ocean, does it go further than the crust?
No, the ocean would be kind of like, picture this is the crust, and then picture kind of a dent in the crust, but not clear to the mantle. Okay.
So it's like super deep, but the crust is a lot deeper than it seems.
That's true. The crust is a lot deeper than it seems.
So it's like miles?
It varies on the Earth's surface. You know, mountains, the crust would be higher,
Yeah.
and then, like you're saying, the oceans, the crust would be thinner.
Yeah.
Actually, with the oceans, at some point, maybe that's where the crust, and you kind of get these kind of fissures where you can get materials coming up. The Hawaiian Islands.
So like underwater volcanoes?
Yes, underwater
Is it where it's
volcanoes.
like- So does the ocean get warmer the further down you go?
How does that work? I think if you're not in the it gets cooler. It gets cooler mostly because you're getting farther from the sun. Yeah. But there are definitely some hot springs, some hot spots where the ocean would be warmer. Yeah.
Have we like drilled to the mantle?
Have
Is
we
that too
drilled
far?
through the mantle? I don't know. But again, the mantle's thickness changes where you're at on the Earth's surface. Probably. I have to think about that.
Because I mean, that'd be like a good, you could get good data out of that, right? I don't know.
Right, yes, yes. And the history of our Earth is so wide, though, depending upon what part of the Earth you're kind of drilling into, though. Those are great questions. So convection is one way to cool off. Conduction is the next way to cool off, and I don't know if you see this. I'll add it. So this is this little kind of, from the mantle through the crust is B. That's called conduction. Okay, so here we have, let me choose black. This is A, getting energy out. This is B, getting energy out. It's conduction. Conduction is very similar to if you have a pot of water you're boiling on the stove, and if your handle happens to be metal, what happens to the metal? Heat transfers, yeah, that's conduction. And then the last one is radiation. Oh, electromagnetic radiation. Radiation, those cousins. It's free. The energy basically goes at the speed of light in all directions. So that's radiation. That's wonderful. So that's one way that the terrestrial worlds and moons have cooled down over time, all of them. And I think I might have mentioned this before. Let's see, I'll put this whole thing up here. Whole thing up here. If I'm holding the Earth here in my hands, and if I go from the polar regions and I basically go like this, okay, that's my way of saying this magnetic field, okay? Now, magnetic fields they affect magnets, okay? Or they affect compasses. Magnetic fields can be created by, there's just a battery right here, you kind of see the copper top. Okay, this is a battery, and one of the things about batteries is they're great at taking electrons, having electrons go out, and then electrons come back in. That's what batteries do. So basically picture these electrons going out, and this is a copper wire, and then they go back in. That's all that is. Okay, so a battery, electrons out, electrons in. So the thing here, though, this figure's done, I'll put E out, E in. The thing about this is it's basically taken it and it's woven it around a cylinder. So now what you have is electrical charges going like this, like that, okay? They come out, they go and then they go like that. Now when electrical charges are doing this, they create, those electrical charges, and I don't know a lot about it, they create a magnetic field. Electrical charges doing this create a magnetic field. They create a magnetic field kind of like you see there, kind of out of the poles of how they're circling. Okay, so magnetic field. Okay, all right. So here we go. What does that have to do with planets? Well, this last one kind of shows you what that has to do with planets. Again, the gray thing you guys told me is the core. Now, it's hard to see, but can you kind of see a little gray thing and then kind of a bigger gray thing? Okay. We actually have two parts to the core, kind of like the movie said. We have a solid part of the core, and it's solid because of the pressure. And then we have a liquid part of the core. Okay. So, actually, within the core, does it have light stuff or heavy stuff in the core? Heavy stuff in the core. Yeah, heavy metals in the core. And so these metals actually kind of act like those electrons chasing each other around. Okay, so we have the solid core, we have the liquid core. The liquid core actually is what kind of makes this kind of electrons kind of jostle. Is our Earth spinning? Yeah. So actually it's the Earth spinning that kind of gets these electrons in the metals that are molten kind of doing their thing. So that all kind of goes together to make electrons do that, to make this. And that's my magnetosphere, magnetic region. And you can kind of see it there on the Earth.
Don't compasses go haywire in like different parts of the Earth?
Could be. I'm not real kind of familiar with that. Compasses going haywire at different parts of the Earth. Probably, I don't know. I know they go weird, like wacko around the Bermuda Triangle and everything, so I don't know. That's a whole other thing. But, so, here we go. You can kind of see the ghosty sort of thing. Of course, this over here is the sun. This yellow is the, what's that? The solar wind. That's the solar wind, exactly. And you kind of see the ghosty part here. That is the protective magnetic field that comes from the spinning, the molten part spinning, okay? Actually, the way this diagram is do you see the green thing? I don't know, it looks green to me. That actually is the little Earth, kind of drawn to scale here. Is our magnetosphere very big? Yeah. Yep. So that's the Earth, and that's the Earth's magnetic field, called the magnetosphere. Now, Dr. Van Allen actually is, I don't know if you're familiar, probably not, he's from Mount Pleasant, Iowa. Dr. Van Allen. And I'm pretty sure he spent time or had digs at the University of Iowa, an astrophysicist. And it was him that actually came up with this idea that not only do we have a magnetosphere, okay, but we have regions, and they're here kind of in pink, kind of regions, kind of going around the Earth like this. They're called the Van Allen belts, after Dr. Van Allen, okay? And the Van Allen belts are great places for, they're kind of the last stop for stopping some of these charged particles coming from the sun to getting to the Earth. Okay, they're Van Allen belts. They're basically, like I said, they're kind of the last stop for electrons, so they don't go through the Earth. They're coming from the sun. Okay, not electrons, charged particles, high energy particles coming from the sun. They get caught up in our magnetosphere, but they kind of get deposited in our Van Allen belts. Okay. So the Van Allen belts, actually, there's this cool phenomenon. Anybody in here seen Northern Lights? Well, it's on my bucket list. So the thing about our magnetosphere, okay, is it kind of has a couple weak spots. It has a weak spots at the poles, okay? So it can stop charged particles, but if there's too many charged particles, actually our Van Allen belts kind of become overly populated with charged particles from the sun. They kind of ooze into the polar regions, and as they go through the polar regions, they fall through Earth's atmosphere and they glow. Okay, that's it. That's the Northern Lights. Okay. I've had discussions with different people who are like, well, Northern Lights, actually you can see them, if this is the Earth, you can see Northern Lights, you know, here at the equators. And I'm like, probably not. I don't know, not as I understand it. So if they're saying, hey, this is a great time to see Northern Lights, the closer you go to the pole, in our case the North Pole, the more likely you're going to see the Northern Lights, kind of glowing. So that's Earth, and that's kind of, we have a magnetosphere, okay? Okay, switching gears a little bit. A lot of these things, like, totally make sense to you. So, like Earth's surface, science is all about observations, and one of the things we need to do is observe what Earth's surface looks like now, and it will tell a story, okay? Not just Earth's surface, but the moon's surface and the other terrestrial planet's surface. We definitely have craters on the moon. Let's pick on the moon. We got craters on the moon, okay? We don't have as much craters on the Earth, and that has to do with kind of the weathering over the years, okay? Volcanism on the Earth, volcanism, volcanoes, okay? They definitely do their fair share of kind of changing what Earth's surface looks like. And it kind of goes back to, can we dig down and kind of see what the layers of the volcanic lava and stuff like that? Yes, we can. We can go back in time to kind of see what Earth used to be like. Plate tectonics, I kind of mentioned this the other day. I like to think of kind of the lithosphere as being kind of the slabs that are kind of sliding on this mantle, okay? That has resurfaced Earth over time. And erosion, we actually have wind erosion and we have water erosion kind of doing its thing on Earth's surface. And Earth is unique in many of these things, but not all of them, with regard to kind of another terrestrial planet or a moon. So here on the left, this is an artist rendition of, and I like this left one here. It kind of says you can have something small make a large impact, okay? So think of kind of the moon and our impact craters. But this right here, this is actually, I don't know if it's anybody ever been here to Winslow, Arizona? Song about that.
I've been through there.
You've been through there?
Yeah.
But here, yeah, it is very cool. This is actually an impact from a crater a long time ago. So, and it's relatively recent, like 50,000 years. That's recent, right? And so there hasn't been time for it to be weathered away or plate tectonics.
Feel really recent.
No, it doesn't feel very recent, but it is
So I
compared
guess
to.
that's why everything,
4.6
there's like, looks like
billion
there's like
years.
nothing around there.
Yeah, it looks like there's nothing around there. Now, it is in the desert, so
Maybe
So
that's
it's
why
just
it's
a
desert.
very arid, yeah. Very arid. Okay, so, this to me here on the far right, to me it looks like a figure, doesn't look like a photo. But what it's trying to show is a little bit of volcanism. Do we have active volcanoes on the earth? Yeah. I listened to a podcast the other day about supervolcanoes. Scary, I'm just saying. So we've been talking about the mantle. Is it really liquid? No, not necessarily. But in this podcast on supervolcanoes, there are these times when the volcanic eruption doesn't have the slow-moving magma. It has, I think it's pyro something, but it goes really fast. Pyroplastic, maybe. It goes very fast. So you kind of see that. And this looks like Mount St. Helens, yep. Okay. So the whole dust thing going up into associated with volcano going up, do you think that has consequences with regard to Earth's surface, Earth's atmosphere? Yeah, it does.
Acid rain.
Acid rain, yes, volcanoes and acid rain, yeah, exactly. The whole thing about the supervolcanoes, the particulates associated with the smoke from the explosion are years in kind of making things die off. And
So what's the difference between a regular volcano and a supervolcano?
regular volcano and a supervolcano. Supervolcanoes are much less predictable than regular volcanoes, I know that. And supervolcanoes, it's kind of a magnitude thing, like it's on a scale of, I don't know if it's 1 to 10, and then 8, 9, and 10 would be the supervolcanoes.
Okay.
But
I guess we wouldn't know, but would Pompeii probably fall in that category?
I think so. They did mention Pompeii. And actually, we have a simmering supervolcano in the Yellowstone area. And I think when they said if that one went off, it actually would directly affect from New York to the West Coast. So that's kind of with the direct impact.
From coast to coast,
Mhm.
it would,
Mhm.
oh my gosh.
Yeah.
They
So
stick a cork in it or something?
I don't know. I don't know. She said, yeah. So yeah, it's kind of scary. So still Earth. Looks like Earth, doesn't it? Grand Canyon? Been to Grand Canyon? No? Okay. And the Colorado River, right, basically over time etched down through that water flowing, eroded, and made the Grand Canyon. That is so cool. I mentioned glaciers kind of coming down from the poles and retreating. They've definitely kind of changed the surface of the Earth. Wind erosion, kind of seen on with the sand dunes, and then water erosion for the last
Wait,
one.
that little river up there is what they think made the
Colorado River?
Yep.
Well, it's that size now, but over time, yeah.
That it had to take so long.
Yeah,
Like,
yeah. To carve that out. Yeah. And it's just amazing to think that as you go down, you're going back in time. I just think that is so cool. It's amazing. Yep. And this one is talking about plate tectonics. So of course the orange stuff here is the mantle. Okay, kind of a slow-moving plastic sort of thing. The red-orange is the mantle, and kind of this tan up here is the crust. And the crust is broken up into plates, that's the term plate tectonics, and there are actually a couple of, maybe even 3 plates being shown here. Plates can do a few things, okay? let's see, we'll call this plate A. I'll call this plate B, and I'll call this plate C. Okay. So we kind of have them moving. We have, can you see where A and B, starts with letter C, are converging? A and B are converging, and B and C are diverging. So as they move, then we can have things like earthquakes, and actually in the boundary of where they move, we can, if they move enough, we can actually have liquid mantle or magma coming up from where the fissure is. So the Himalayan mountains, road trip, are actually a place where two plates are converging. And then here it's showing you two plates diverging, creating the Red Sea. And it's kind of neat where plates are diverging, and this maybe is kind of what we were talking about. Basically, stuff has to come back up to replace the deficit.
So we're standing on a ticking time bomb pretty much.
What, the Earth?
Yeah, at any point it
Yeah.
could just explode into like lava,
Yeah.
theoretically.
Theoretically. And then California, if this is California, actually is on converging plates. But there's a subduction zone. So basically, instead of kind of cramming, making a mountain, the California, yeah, exactly. California is going up and over the plate, the Pacific plate that's coming under.
Places of California is gonna get like sheared off.
No,
Like-
California is going up and
Oh.
over, and
Oh,
stuff
it's
is,
gonna-
yeah,
oh,
it's a
so it's on the
subduction
other
zone.
side of it.
Yeah, so this is the Pacific Ocean is coming underneath. So, yeah, I think so too. Love those plate tectonics. Makes life interesting. Okay, so Earth's atmosphere equals protection. Do all planets have atmospheres? No. I like that little video we saw because on with regard to Mars, the whole terraforming thing, you know, right? Okay, so the Earth's atmosphere now, it hasn't always been this way, but you're looking at about 80-20, so about 80% nitrogen and only about 20% oxygen. Carbon dioxide, it's there, but it's kind of in varying amounts. Okay, so I think we talked about this a little bit before with the squiggles are actually coming, think of them as coming from the sun. Squiggles are coming down. Down here at the bottom we have the Earth's surface. And how far the squiggle goes means how much it can penetrate the Earth's surface. Okay, so here we have X-rays. Can it penetrate Earth's surface? Oh, sorry, penetrate Earth's atmosphere. No, it's stopped up here. How about ultraviolet? It can go a little bit more, okay? How about visible light from the sun? Can it go through Earth's atmosphere? Yeah, so that's kind of how it works. And we actually talked in chapter 5 about these are cousins, right? We have X-rays, ultraviolet radiation, and visible light. They're all cousins.
So, global warming,
I'm coming up on that, but
the light comes through and then it doesn't escape.
global warming basically says, well, first off, like if you have a car on a sunny day, let's make it, you have black interior and it's a sunny day. What happens when you go to get in your car? After it's been out there a few hours, it's hot. And this is kind of the whole global warming thing. Basically, visible light came through your windows, it interacted with your upholstery, okay? And then that warmth warmth is infrared radiation. That radiation doesn't go through your glass panes as well. So you have light coming in, light heating you up, it changing to a longer wavelength, warmth, heat, okay? And then basically your glass insulates against heat leaving. It doesn't insulate against light coming in, but insulates against heat leaving. And that's the problem with carbon dioxide, is basically carbon dioxide says, light, come on in. Carbon dioxide says fine, but he says thermal energy, I think I'm gonna heat up, basically with that thermal energy. So light comes in from the sun, it heats up the earth, and then that heat can't get out. So, yep. All right. So terrestrial worlds. Oh my gosh, my mom is so fascinated with the whole planets that were found. So we talk about that. I told her we were going to talk about planets today. She's like, oh, are we going to talk about those new planets they found? I'm like, no, Mom, we're just going to talk about normal planets. Okay. But this whole idea of having the protective atmosphere, as we look at other planets to colonize, or if we look at other planets, can life survive? That whole atmosphere is kind of critical to kind of keeping these energies that are harmful to life. We know X-rays and ultraviolet radiation, okay, they kill organisms. Okay, so you need that atmosphere. All right, so one of the things I wanted to cover at this point, while we were talking about atmosphere, okay, is this whole idea of the skies being blue. We're going to see some photos of, if you're on the planet Mars, what does the sky look like? And actually, it's kind of pinkish. I know. And the Martian sky being pinkish is a direct influence of its atmosphere. Actually, instead of nitrogen, oxygen is carbon dioxide. It's a thinner atmosphere. It's not as thick. Okay. But Earth's nitrogen and oxygen, basically what happens is those gas molecules, how do I say this? This would be incoming, not actually light before it gets to the Earth's surface. Basically, the Roy G. Biv, BIV stands for what? Yep, blue, indigo, violet. Are they short or long wavelengths compared to red? They're short. So these short wavelengths, actually, of visible light coming from the sun, they ping, it's kind of like the little nitrogen gas particles kind of act like ping pong balls. And so those energies come in and they kind of ping around, those short wavelengths. And they kind of ping around and they make the sky appear blue. Isn't that cool? I love it. So we call that a scattering effect. And so actually then, when the sun is low on the horizon, you get an extra dose of scattering. Because if the sun is low on the horizon, and we talked about this before, basically the sun's light has to come through more of the Earth's atmosphere. So you have ping, 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 ping out there. So basically your BIV is all pinged out. So the light that finally gets to you is your longer wavelengths, your Roy Gs. Roy Gs. So that's kind of why you have those. That's that. All right. Hey, Logan. Logan. You're fine. You need to wake up, hon. Okay, so this actually gets to the other planet sort of thing. When we look for something where life can be, we need to kind of look for something kind of like Earth. And you've heard kind of like one of the things about Earth is, well, there's a number of things. One is temperature. So Earth has had for some time the greenhouse effect going on. We are so grateful for the greenhouse effect. Greenhouse effect is just kind of like the car I told you a minute about. Greenhouses are great for having plastic or glass, okay, that basically light can come in, okay, it interacts with your plants or whatever and heats up the room. That's what a greenhouse does. Light comes in, it heats up the room, and then that light, it heats up the room, that heat, okay, that light has been turned into basically, doesn't escape, your glass kind of stops it from leaving like that. Acts as a thermal barrier. Okay, so that's the greenhouse effect. Let's see. So things that kind of are good at kind of making Earth's heat stay with the Earth, okay, that comes, the heat from the sun, that energy that comes from making us nice and warm. We mentioned carbon dioxide, but also water vapor is a greenhouse gas. Who knew, right? Water vapor, like, sometimes the air is dry, sometimes the air is humid. Water vapor is good at trapping heat. So we're glad for that. Oh, I should have put this up here. So you kind of see the big, kind of go from left to right. This is the squiggle, this thick squiggle is from the sun, okay? This little less squiggle is going out. Can you see it's less? Okay. That means that some of that sun's energy was converted to something else. Now these red squiggles are heat. Okay, there you go. And those particles are greenhouse gases. Does that work for you?
So we're worried about like our thermal barrier getting too thick.
Right, we're worried about what's called a runaway greenhouse effect. So the greenhouse effect's been here like forever. The Earth's had carbon dioxide. The carbon dioxide levels have gone up and down over the eons of time. okay? I will say, and I have a slide coming up here at the end that talks about the runaway greenhouse effect. And if this is CO2 going up and down and up and down, we're gonna see why it just naturally does this. Here at the end, it goes up like that. Okay, so CO2 levels is really spiked ever since we've been burning fossil fuels since the Industrial Revolution. Okay, so that's what we're kind of concerned about. So this is kind of neat. I like this. Kind of, we have, let's see, Venus, Earth, and Mars. Closest to the sun, okay, wait, no, Mercury's closest to the sun, but Mercury doesn't really have an atmosphere. Venus has a very thick atmosphere. Earth has a pretty good, a healthy atmosphere, and Mars has less of an atmosphere than even Earth. So what the columns do is, if you go to let's see, how do I say this? This one right here, the middle column. That's how warm the planets are. Okay, Earth on average is about 15 C. It's weird to get one temperature for a planet, right? It's kind of strange. It's statistics. Okay, and this tells you if Earth, let's see, if Earth did not have the atmosphere it has, it wouldn't be 15 Celsius, it would be negative 16 Celsius. That's cold. Okay, but with the Earth's greenhouse effect, adds a 31 degrees on it. See how that is? Basically, you take this plus this, like negative 16 plus 31 gives you positive 15. So if we look at Venus, which has got a crazy atmosphere, check this out. It is really hot. Okay, it's 470 degrees Celsius, pretty constant, the daytime side and the nighttime side of Venus, because it's thick clouds act like a great blanket. Okay, notice if it didn't have its thick clouds, it's farther from the sun. Wait, no, it's closer to the sun. It would be a negative 40 degrees Celsius. I know. So it's like, it's got more of an enhancement, 510 degrees Celsius, because it's got thicker atmosphere.
Can plants live at that temperature? No.
Can plants live at that temperature?
Any kind of.
I bet so. I don't know, but like there's this thing called extreme ophiles, like extreme whatever, and ophiles meaning they love it. So extreme ophiles can live in some crazy conditions.
I mean, yeah, like what if we introduced them and they started filtering out the carbon?
I know. I don't know, but that we bump up against our planetary "thou shalt not screw up the planets." We talked about that, but it might happen. And then Mars has a thinner atmosphere, and so actually its greenhouse effect only adds 6 degrees to its surface temperature.
Pretty good step up though from 50 degrees below.
That's true. That's very true. That is very true.
Oh, they won't let us put other stuff on other planets? Like,
Nope, they won't let us. Right now, we can't put other stuff on other planets. Well, it has to be done tastefully. We've left stuff on Mars, we've left stuff on the moon, but it has to be so that we don't think it interferes with the current ecosystem.
Yeah, that's what I mean. They're like, we can't put like a fish from our planet on like another
Not supposed to.
planet.
Not supposed to. I was out at NASA's site kind of looking at that. It's planetary protection, but it's both ways. Like, thou shalt not bring anything, microorganisms back to our planet. Though we brought moon rocks back. But, so.
We are very good at following it.
Yeah, rules were made to be broken.
I mean, why are we even discussing terraforming Mars at this point if that's the case?
I know. But we haven't implemented it. I mean, there are, so.
Is that just like what the government says? So if a private corporation did it, then it's like, oh.
It is new territory, you know. So I think the rules are gonna have to be made up as we go a little bit, you know. So, 2 gray photographs. This one is the moon, and this one is Mercury. To me, they kind of look similar, yeah. So Mercury, now we're gonna kind of step through some neat facts about these objects. So Mercury has a very thin atmosphere, where the moon basically has no atmosphere. I've heard the moon's atmosphere described as an exosphere, which basically means it's kind of oozing some gases, but the size of the moon and its gravity is not strong enough to hold those gases there. They kind of fizz out into outer space. They have a fair bit of cratering, means that there wasn't anything to resurface them. There wasn't the erosion, there wasn't the plate tectonics that we see on Earth. Okay. Okay. Now, I'm marching towards the moon. This down here, by the way, I'm pretty sure I got this right. Have you ever seen this white thing down this, like this right here? Kind of that, through binoculars or anything? Go ahead and call that what I think it is. This is a crazy crater called Tycho. I have a friend at the observatory who really likes that crater, and I agree. Before I go much further, let's see, how do I... Well, do you see the dark parts? Okay, good. So the dark parts are actually kind of low parts, and sometimes these make out of, like if somebody says, oh, do you see the face in the moon? What they're saying is, do you see kind of those dark parts make out a face? I'm not sure I do. I've heard the rabbit in the moon. I can almost kind of see the rabbit, like this is the ears. Okay, but if anybody says, do you see an image, they're probably asking, do you see those dark parts? They're kind of lower regions. Those dark parts, the words for them are called mare. They are mare, and mare is Latin for seas. Okay, so the dark parts are mare. What's that? Seas. It means seas. Yeah, like sea. Have you ever heard of like the Apollo missions landed in the Sea of Tranquility? It was a mare of tranquility. Exactly. And those white regions are highlands. So the white regions are highlands. I'll just put, yeah. We already talked about the synchronous rotation. We have the near side and the far side of the moon. And I'm not going to give anybody a hard time or anything, but I got this poster from one of y'all. On one side is the side we see, on the other side is the side we don't see. And I know you guys can't all see it very well. But which side looks more cratered? The left or the right? Looks more cratered. Then the dark side, the dark are the mare. Can you kind of see the mare here? Okay, these have names on it. And so this actually is more cratered. This guy over here is the far side. This guy over here on the left is the near side. Okay, far side and near side. And a moon map will actually kind of give you little names for those things. So isn't that cool? So we don't ever see that far side. This is the side we don't see. Why? It starts with letter S.
Synchronous rotation.
Yes, synchronous rotation. So this is the far side, not as in the comic strip. And this is the near side. All right? Okay.
It's like really cratered.
It is really cratered. The far side is really crazy cratered. So the dark regions are the mare and the light regions are the highlands. I guess I could have put that up there, couldn't I? Let's see, what else did I say? Okay, so this one, and actually if you look at my moon videos, you can actually see this, I think, kind of. But let's pick on this right here. I'm trying to kind of show you over in the right here. So can you see that? I call it a belly button. Do you see that thing in the center? I call it a belly button. That actually is what we call the central peak. That's the central peak. The belly button. The terraced sides, and it's kind of hard to see with this one, but with other pictures you can see, and you can kind of see on that one, where it's kind of steps up. It's like kind of steps, like you're in the bottom of the crater and you're stepping up. Okay, that's terracing. The ejecta blanket, we can pick on Tycho for the ejecta blanket. Oh my gosh. That's kind of the bit of material that got strewn as upon impact. Okay, so all of that splashing out part, that is the ejecta blanket. Isn't that cool? And the whiter whiter, as in the color white, the ejecta blanket, the newer the impact. Very good. So is the moon, do you guys remember the other day, is the moon geologically active? No, not now, nope. But actually, the way it's got the mare, we think that it used to be, well, all of the terrestrial planets used to have, and I say liquid, but actually I'm kind of talking about that kind of plastic looking stuff that makes up the mantle. All of the planets used to be a little bit ooey gooey. So this is actually kind of showing you how the mare formed when the moon was young. When the moon was young, it, like everything else, had kind of a crust, okay? It had a core, it still has a core and a crust, okay? But the mantle part wasn't solidified. So it's thought that early on in the moon's history, it got struck, and you kind of see here, this is the impact crater here, the second slide. This actually is from below the crust, where it's just kind of, it's been thinned out, and you have a little bit of mantle coming up and making your flat mare. Okay, and this is what it is today. So that's kind of how we think that all happened. Okay, Mercury. Let's finish a little bit with Mercury. Actually, this hollows thing I was getting ready for today's lecture, and I looked up hollows. I typed in Mercury hollows, and they are kind of cool. So actually, if you go on the Twitter feed, I have a link there that will take you to the hollows that are kind of interesting. So this is Mercury. It looks like it could be the moon, but it's really Mercury. Can you see this left one here? Kind of, and I'll kind of pull up a red pen here. Do you kind of see this sort of region right along there? Okay, that's a place where it's like lower here and higher there. I've heard actually this also called a scarp. I like that name, scarp. Okay, and it's thought that it kind of happened while as Mercury cooled. All right, well, that's a good place to start. We for sure will finish this chapter. You guys have some great questions on Friday. And we might start the next chapter, we'll see.